Hello and welcome to another weekly edition of Aldehydes and Ketones, the #1 show on YouTube. So talking about two new functional groups here, the aldehyde and the ketone, and they're very similar in terms of structure and appearance, but their one small difference ends up being a pretty big difference. So we'll talk about the reactivity of these in general and then the differences between the two structures. So what we have with the aldehyde and ketone for this chapter is we have a polar pi bond, right? So this double bond here is between a carbon and an oxygen. So there's a carbon-oxygen single bond, which we know is strong, and there's a pi bond there as well, right? What we also have is no clear leaving group for this reaction, right? So there's no piece of this that's going to come off easily. There's a double bond to oxygen. You have to break two bonds to make that go away. That's going to take a bit more work. If we imagine breaking off hydrogen as H-, that's a really, really reactive, strong base, so that's not going to work as a leaving group. And an R group, so any generic carbon, think methyl anion there. Also, that's one of the most reactive things as well as a negative charge. So not really any leaving groups on either side. But we have a pi bond there, which is going to be more reactive in general than a sigma, and we have a polar bond in both cases too, right? So we have potential reactions with nucleophiles or electrophiles. So let's start there. Both aldehydes and ketones have carbonyl. That's just the generic term for carbon double bonded to oxygen. If we're talking about that in isolation, that's a carbonyl. It's not really its own functional group. Something else has to be bonded to it, which then defines what we call it. Right, so they both have a polar bond, so they both have a positive charge on the carbon, which can be attractive to nucleophiles. So something negative with some electrons to donate, it might go there. And that ends up being one of the main categories of reactions of aldehydes and ketones, which is nucleophilic addition. They're actually pretty versatile, so there's a bunch of different reactions they can do, but that's one of them. That's one of the main ones. So I have a dipole. It's potentially electrophilic carbon, right? So a nucleophile could come in there and add and do a reaction, and subsequent videos will show a bunch of different reactions, both with strong bases and with weak or strong nucleophiles, and with weak nucleophiles. There's a lot of variety there. But I'm going to talk about the chemistry between the two, right? So if we're comparing the aldehyde and the ketone, a good question would be, well, which one is more reactive to nucleophiles? Right, so nucleophile can add there because you have an electrophilic carbon. If the nucleophile adds, the pi bond could break. In part, that's going to happen because there's no other good leaving group in either aldehydes or ketones. Breaking this carbon-carbon bond would be really unfavorable. Breaking this carbon-hydrogen would also be pretty unfavorable. They're really bad leaving groups, right? But so which one is going to be more reactive? Well, the only difference we have here is there's a hydrogen on one side for an aldehyde and another carbon of some kind. It doesn't have to be a methyl. It could be a different branched carbon, but another carbon on the other side for the ketone. So we have to kind of look at what do we already know about a methyl group attached here, right? And we do actually know quite a bit. So from looking at carbons in the past, we know that they are weak electron donating groups, right? So just by nature of having two methyls instead of just one, right? So this methyl group can donate its electron density. Hydrogen doesn't have any extra electrons other than what's bonded here. Having two groups here, both doing inductive electron donation versus only one, right? That's going to add electrons to this carbon potentially, and that's going to make it less positive, right? So the weak electron donor is going to slow down the reaction because it's going to make the carbon less electrophilic. Right, it's sharing those electrons, but the more positive it is, the more reactive that's going to be. The other piece is here, and the reason why I drew it out long form instead of just sticking with the abbreviations is, all right, well, that carbon has 3 hydrogens attached compared to this hydrogen here. Right, so this hydrogen is very small. Right, so it's relatively no steric hindrance. Right, it doesn't really get in the way as much. Right, this nucleophile has to find its way to that carbon to do an addition reaction. So it's going to add directly while all of these bonds are still in place. Right, the more stuff you put here, and this is the smallest ketone we could get, but as those carbon groups get bigger and more branched, you have more stuff in the way, the slower that reaction is going to go. Because for an addition reaction like this, remember these atoms need to find each other in space. Right, these have to work their way through the solvents and collide in just the right orientation to make that change. Right, so smaller, less steric hindrance there, that's going to make a difference. Right, so the ketone has more steric hindrance. It has a weak electron donor. It's going to do reactions slower than with nucleophiles. So for a nucleophilic addition reaction, right, the ketones are going to react slower, the aldehydes are going to react faster. When we look at other functional groups like carboxylic acids and esters and acyl chlorides, which also have a carbonyl, we'll be able to look at other factors and things that can react even better or sometimes even worse than these. But those are a lot of the determining factors, things we know, right? So pi bonds are more reactive. So if you have a polar pi bond, the nucleophile will add to the positive end, but that pi electron bond is the thing that's going to break, in part because there's no good leaving groups on either of these functional groups. And then comparing the reactivity, right, so since they both have the same dipole, carbon double bonded to oxygen, the reactivity difference is going to be small things like lower or greater steric hindrance and increased electron donation, weakening the electrophile. Right, so it's a new functional group using things that we already know, and then in future videos we can look at the reactions they can do with nucleophilic addition as one possible way for that to go.